Okay, key issue 1 is how do geographers describe where things are? Geography, if you take the word and you break it down, geo means earth, graphy means to write about. So that kind of tells you what it's all about. Geography is a study of where things are found on the Earth's surface and the reasons for those locations. Human geographers ask two simple questions. Where are people and activities found on the Earth? The second one is why are they found there? And I'm going to propose that we add a third one to this. What are the effects? So going forward through the rest of the course, there are three questions that I want you to remember. Three questions that I always want you to ask. That is where, why, and what are the effects? Where, why, and what are the effects? And you'll hear me say that quite a bit in class. Let's talk about maps a little bit. Map. Two-dimensional or flat-scale model of the Earth's surface or a portion of it. Cartography is the science of map making, and maps, they serve two purposes. It's a reference tool to identify an absolute and relative location, which we'll get into a little bit later, and it's a communication tool to show the distribution of human activities or physical features. Maps have been around for thousands of years. The earliest maps were simple navigation devices. How do you get from point A to point B? The first map was prepared by Aristophanes. Later on, improvements to the world map would be made by Ptolemy. After Ptolemy, advances in cartography primarily made outside of Europe were by the Chinese and Muslims in the Islamic world. Later on, it was revived during the age of exploration and discovery. Sailors had to figure out, how do I get from here to here without, dying of starvation or thirst, getting lost in the middle of the ocean? What you're looking at here is an ancient Polynesian stick chart. This was used by the Polynesians in the Marshall Islands to travel literally thousands of miles between island and island out in the open seas. It showed the swells, the currents in the oceans, decorated with sticks and with shells. This is Aristophanes' first map of the world. As you could see, some things he got right, some things he didn't, but that's before data imaging and satellite and remote sensing did a pretty good job right here. This is Al-Idrisi's map. He was a Muslim scholar. As you can see, it's a little bit more detailed. A few more things on here. And the basic shapes of some things they have wrong, but you can see it's an improvement. Later on, this is Ortelius's map. As you can see, this shows both the eastern and western hemispheres. You have the New World here, North and South America, as well as Africa, Asia, and Europe. So things got a little bit better during the time of discovery. Contemporary maps. Okay, that's a shift from simply a tool that provides a location reference to a tool used by geography to show complex data, complex geographic phenomena, aka more information. We're going simply from saying, how do I get from point A to point B, to let's show different things and different amounts of data. What you're looking at here is a map. You look at the title, September 11th flood extent. This is in New Orleans. The city here, the parish, the French Quarter, famous French Quarter right off of Lake Pontchartrain. And this map shows you many things. If you take a look, you see the flooding is represented here. You see interstates and roads. You see the Mississippi River, Lake Pontchartrain. You have your scale. So this is more than simply, how do I get from point A to point B? This is showing you flood damage in the city of New Orleans. This map here, percentage of African Americans in that same area. And you see the different densities, 75 and above in the darker density, 41 to 75 here, 15 to 40, and then in certain places less than 15%. This information is used to convey here are certain people in certain ethnic neighborhoods, which we'll talk about in later chapters. But once again, a map that is showing more than simply how do I get from point A to point B. Take a look at this one. Population change since 2000. You see where some residential neighborhoods, over 50% of the population has left. Why? Because of the flooding from the hurricane. Some of those areas are damaged irreparably, beyond control, and the population, the people just have simply not come back. Here you see a photograph of some of that damage during President Bush's time. Hurricane Katrina. Let's talk about scale. And this is something a lot of people get confused about. When you use the word scale, it can mean many different things, but when we're talking about basic geography and maps, map scale is the level of detail in the amount of area covered on the map, and it's the map scale. Let's say it a different way. It's the relationship of a feature's size on a map to its actual size on Earth. How big is it on the map compared to really how big is it on Earth? Map scale can be shown in 3 different ways. You can have it as a ratio or fraction, and you see this quite often, 1 to 24,000. The number on the left is 1 unit of distance, while the number on the right represents the same unit of distance on the Earth's surface. Another is written. You can simply say 1 inch equals 1 mile. Numbers on the left is 1 unit of distance, while the number on the right represents a different unit of distance on the Earth's surface. Then there is graphic scale. That consists of a bar line marked to show the distance on the Earth's surface. So you have a fraction or a ratio, a written scale where it simply says 1 inch equals 1 mile, or a graphic scale, which is usually a bar line marked to show the distance on the Earth's surface. And that's, people always will measure that and plot the distance when looking at a map. So take a look here. You see this is southeastern Texas and Louisiana, and you see your fractional or proportional scale right here, 1 to 10 million. Okay, and then of course the actual scale in miles and kilometers there, and it's highlighting one area. The Houston metro area, once again, 1 to 1 million. It's focused a little bit more, a little bit narrower, and as you can see, not the same amount of distance. The central Houston area, we've narrowed this even further. This is 1 to 100,000, and we're talking in feet or meters. We can go in even closer with Google Earth. Minute Maid Park, that's where the Astros play, not where they hand out free orange juice. This is 1 to 10,000, and we're talking here in feet. Today's technology, they can actually read the headline of the newspaper that you're reading if you were sitting here in the stands. They could tell if you had sunglasses on or not, what color hair you have. So it's pretty amazing the way things are today. Let's talk about projections. Scientific method of transferring a location on the Earth's surface to a flat map is called a projection. Okay, it's a projection. All maps are called projections. Earth's spherical shape causes problems. It causes distortion. You cannot take a globe, and a globe actually is one of the most accurate depictions of the Earth that we have, but you can't take that, wrap a sheet of paper around it, and come out with a perfect map. There's no way. Every map has its pros and its cons. It has things that benefit that map. Some maps are very specific to certain things. We'll talk about those in a little bit. Some maps are more distorted than others, but every single map has distortion. There are 4 types of distortion. It could be the shape. It could be the distance between points. It could be the relative size, or it could be the direction. So once again, the 4 types of distortion are shape, distance, relative size, and direction. What we're looking at here is a Mercator projection. Now you can see this is a very classic grid system. All of the grids of latitude and longitude are very accurate here. What is the pro to this? Well, if you're a seaman and you navigate using the ocean, this shows you your latitude and longitude very accurately. And this is actually preferred by people who travel on the water. But look at Antarctica. Is it really this big? No. Obviously here, one of the cons with the Mercator projection is that you have big distortions at the poles. Okay, it's good for water navigation because of the clear grid system, but distortion at the poles. This is the good homolocene projection. Sometimes this will be called an equal area projection. What it tries to do is accurately capture the shape of land masses and also accurately portray the size of land masses. But in order to do so, they've had to chop up this map. This is not. You see that there are obviously gaps here and here and here in this map. So if you're using this to travel by the ocean, you get problems. But what it does show you is that, Africa really is this big compared to the Middle East. Latin America and South America. This is the actual size and shape of these places. So like I said, every map has problems, every map has distortions. Some are favored over others for different reasons. This is the Robinson projection. This is what you see a lot of times in classrooms. It still has problems if you look at this, at the size of the land masses at the poles. Okay, still has problems with that. Geographic grids. Let's talk about that for a minute. A geographic grid is a system of imaginary arcs drawn in a grid pattern on the Earth's surface. We call the two lines on the Earth that we use for a geographic grid meridians and parallels. Meridians are arcs drawn between the north and south poles. We call this lines of longitude. Lines of longitude heading north and south. Parallels are arcs drawn parallel to the equator at right angles to the meridians. Each is numbered according to a system known as latitude. Okay, they all start at 0. The value for 0 degrees longitude, or the prime meridian, and it goes all the way to 180 degrees east or west longitude. Values for parallels, or latitude, range from 0, which is the equator, to 90 degrees north or south. So longitude goes from 0 to 180, latitude from 0 to 90 degrees. Take a look here. You have the North Pole, down here the South Pole. The 0 degree of latitude is the equator. The prime meridian is 0 degrees longitude. It goes through Greenwich, England. Greenwich, England right here. That is the prime meridian. A lot of times when we talk about time zones and lines of longitude and latitude, we're going to talk about GMT, or Greenwich Mean Time. We'll get into time zones in a little bit more. But this degree here, 0 degree, or the prime meridian, 0 here, oops, let me go back one, 0 here, but if I followed it opposite of the Earth, that would be 180 degrees. Latitude at 0 degrees heading north to 90, or south to 90. Guys, when it comes to geography, you will have questions on the AP exam that say that if something is located at this degree longitude and that degree latitude, what area of the world would I be in? You have to flat out simply memorize where these things are and the distance. You have to have a complete understanding of longitude and latitude. Points on the Earth's surface can be communicated by referencing points of longitude and latitude, like I said, and here's an example. Denver, Colorado's location is 40 degrees north latitude and 105 degrees west longitude. You have to remember that basic grid system. Let's go back to it again. It starts at 0 degrees here at the prime meridian and 0 degrees latitude here at the equator. Okay, you have to kind of figure where this goes. We'll go do another one. For further accuracy, you can be achieved by dividing each degree into 60 minutes, each minute into 60 seconds. Example, Colorado, Denver, Colorado is the state's capital. It's located at 39.42 north latitude and 104.5904 west longitude. With GPS systems, you can get it down to the foot, to the meter, to the inch. Earth, when we talk about time, Earth as a sphere is divided into 360 degrees of longitude. If you divide 360 by 24 time zones, that means one for each hour of the day, it's 15 degrees. Okay? So for every degree of longitude that you move, every 15 degrees of longitude that you move, you're going either forward or backward 1 hour of the day. Time zones came around as a result of trains, actually. You know, they didn't have time zones forever. And when they had trains, when they were invented, they were traveling so fast they were actually going across time zones. So to make sure there were no accidents and the trains ran on time, trains didn't collide head-to-head against one another, the time zone system was invented. Another interesting thing about time zones, and I'll show you on a later map, is that every country kind of decides what time zone they're in. The United States, for example, has 4 time zones, but other countries have more. But let's get back to this. Divide 360 by 24 time zones. That's 1 hour of the day equals about 15 degrees of longitude. GMT, or Greenwich Mean Time, is located at the prime meridian. That's 0 degrees longitude. It passes through the Royal Observatory in Greenwich, England. And this is the master reference time for all points on Earth. Earth. That is 0. That's where the clock starts. Excuse me. If you head one direction, east from the GMT, you go back in time. If you head west, you're going forward in time. The international date line is located at 180 degrees longitude. The position deviates from 180 degrees longitude at times to accommodate various nearby nation states. As I said, it's not perfectly accurate. I'll show you on a map in a second. Some states kind of wiggle in and out of this line. The point you move on the clock back 24 hours, one day, if you're heading east towards America. It's also the point you move the clock ahead 24 hours, one day, if you are heading west towards Asia. The international date line separates today from tomorrow, today from yesterday. That's where it is. You know, what's amazing is today you can get on a jet and you could fly and actually catch the sunrise at different places on the earth. People celebrate, rich people I might add, celebrate New Year's Eve. They will have the countdown, you know, 5, 4, 3, 2, 1, Happy New Year in one part of the world, fly back across the international date line, celebrate it a second time, which is kind of amazing. Here's that map of the time zones. As I said, 0 degrees longitude is here, running through Greenwich, England. Okay, GMT +1 would go in one direction, GMT -1 in another direction, and sometimes you will see that up here along this line. It'll simply say GMT plus or -1. That means you're either going ahead 1 hour or you're going back 1 hour. As we said, each of these time zones equally or roughly equals 1 hour of time. As you can see here in the United States, we have 4 time zones: Eastern Standard Time, Central Time, Pacific Time, and I just forgot. We'll have to look that one up. Here you see the international date line. Notice it's not straight. Okay, they wanted to separate Russia from Alaska, so it kind of wiggles here a little bit. Some of these other date lines, if you look closely, will wiggle a little bit. They're not exact. It is up to each individual country to determine what time zone they want to be a part of. And some of them choose to be this city or that city in one time zone or another. Let's talk about GIS, or Geographic Information Science. It involves the development and analysis of data around the Earth acquired through satellite and other electronic technologies. When you collect data of the Earth from a satellite, it could, you know, back in time it used to be airplanes, it used to be hot air balloons around the Civil War, but it's known as remote sensing. Remote sensing is simply collecting data from the Earth's surface, from up on high, from up above. Remote sensing can scan the Earth's surface. Individual pixels are transmitted to a station on Earth where a computer assembles them into an image, and then they create maps. Maps created using remote sense data shows a grid of rows, of columns, of pixels, each representing the radiation being reflected on the Earth's surface at a specific point. That leads to GPS, pinpointing locations. GPS stands for Global Positioning System. It's a system that can accurately determine the precise position of something on Earth. GPS in the United States includes 3 elements: satellites placed in predetermined orbits, tracking stations to monitor and control those satellites, and a receiver that can locate at least 4 satellites. And there's the key. You have to have 4 to figure out its distance from each and use the information to calculate its precise location. There's a great James Bond movie where this evil, maniacal villain takes over the satellites and changes the GPS systems around so planes crash and ships sail into rocks and things like that. It's pretty maniacal, but you got to see it for yourself. Applications. You see it in your car. Turn-by-turn directions in vehicles. Navigational aid to pilots and ship captains. And it provides location for social media applications in your smartphone. How many times have you had your smartphone ask you to do a push notification? What does that mean if your smartphone's asking for that push notification? It wants to send your GPS, where you are, up to that satellite so somebody or something can track you. I don't know if you've ever seen this coming through your neighborhood. It is very, very controversial because in some countries they hate this. They don't want to see this. This is a car that Google uses. When you go onto Google Earth and you zoom into your house and your location of your street, This is the car that drives down the road, photographing and filming everything, which is then compared with GPS and then shown on Google Earth. It's pretty funny if you, no pun intended, Google this. You will see that there are many embarrassing photos that this camera has caught of people breaking in, standing in weird positions and awkward stances in their yard. But people sometimes think this might be considered an invasion of privacy. In other countries, they're very hostile actually to this. Some places they won't even let Google drive around and do this. But if you can look up your house on Google Earth, that means that this car or one just like it is driven by, taken that data, taken those images, put it into a GIS or Geographic Information System, and you can zoom in on your own backyard. Layering data, GIS. Like I just mentioned, it's a Geographic Information System. It's a computer system that captures, stores, queues, analyzes, and displays geographic data. And the key to GIS is it shows it in layers. They can tell you so much information, it's almost too much. You like to separate it. You don't want 50 different rows of information for one single map. Maybe you just want to see one or two things on that map. And GIS allows you to do that. You can remove layers, you can add layers. Layers can be compared to show relationships, which is very important. Go back to the ones I showed you earlier about the flooding in New Orleans and then the amount of people in certain areas, you know, how many have left and so forth. You can kind of see correlations there. Data can be overlaid in one GIS from a variety of different sources through a process known as a mashup. Okay, a mashup, and that gets back to that car from Google Images. Here you see some of the different layers of the same map. Vector data, just showing the cities. Okay, here's Fort Collins, here's Grand Junction, here's Durango. Then it shows the highways. You can add more, the landforms. You can combine them into one, and you can separate them out. And it's a very, very important tool for geographers to put information together. Remember, what are the three questions we always ask? Where, why, and what are its effects? This GIS information systems allows you to see the where. When you compare different things of information, you can look at the why, you can figure out the why, and definitely ask questions about the relationships here. What are the effects? Here you see the individual images, the vector data of the cities, adding the highways to that, adding the landforms. Obviously you have mountain, you have Great Plains here, and then you combine it all together. And that concludes Key Issue 1.1. How do geographers describe where things are?